Hello and good evening, everybody, or good morning or good day, depending on where you join us from. My name is Andrei Popescu. As some of you know, every year the Computer Science Committee of the London Mathematical Society, together with the BCS Formal Aspects of Computing Science Committee, are organizing an evening seminar with a talk by a leading expert in an area that lies at the intersection of computer science and mathematics. So in my role as a liaison between the two committees, it is my great pleasure to introduce this year's speaker, Sam Staton. Sam is a professor of computer science and a Royal Society University Research Fellow at the University of Oxford. He has been in Oxford since 2015. And before that, he was in Nijmegen, Paris, and also in Cambridge, where he did his PhD with Marcello Fiore. Sam has well-known contributions to the theory of programming languages and process calculi, where he uses very effectively methods from logic and category theory. He has some exciting new contributions in quantum computing, as well as in probabilistic programming languages. And in particular, he's working on integrating statistical features within programming languages. And in fact, he currently runs an ERC grant called Better Languages for Statistics. Today's talk is titled Programming-Based Foundations for Statistics, where he will explain some of the ideas behind his recent work. I'm sure all of you are very much looking forward to this talk. So I will very soon yield the floor to Sam. But first, let me just quickly advertise another high-profile BCS FACS event. This is the annual Peter Landin Semantics Seminar. This year is organized by Jonathan Bowen and the BCS FACS committee. There's also the annual general meeting that is held at the same day, at the same venue. So this will be a hybrid meeting. It will be on the 6th of December and starts at 4 p.m. So this is at the BCS, the Chartered Institute for IT, and also hybrid via Zoom. More details you can find on the BCS FACS website. The speaker will be Nicholas Wu from Imperial College London. And I will not take any more of your time, so let's listen to Sam's talk.
Okay, well, thank you very much for the invitation, Andre and Jonathan, and Catherine for helping organize this event. I'm going to talk about probabilistic programming, which is one of the things Andre just mentioned. This is the FACS evening seminar, Formal Aspects of Computer Science. So I'm going to take the liberty to approach the subject from the point of view of formal aspects of computer science. And in particular, I'm going to try to argue that programming languages can be a foundation for statistics via probabilistic programming, as I'll explain, of course. Okay, so yeah, let's dive in, and I'll give you a quick idea of what probabilistic programming is. I realize it's an evening talk. Many of you may be eating dinner while you're watching it or whatever, so I'll try and keep it high level, but there'll be a little bit of technical detail at certain points. Okay, so a quick example of a probabilistic program. Suppose we want to model an election poll. We want to know who's going to win an election. Maybe you've followed some elections recently, maybe you've had enough of elections, or maybe you think there should be more elections. I'm trying to get into that sort of thing. But suppose there is an election, and I don't know, let's say I'm standing. It's a very big population, but I do a quick poll, let's say of 100 people. And 51 say they'll vote for me, and 49 say they won't vote for me. They'll vote for the other person, let's say. What's the chance that I'll win this election? Okay. So quick clue, it's not 51%, which might be what you were thinking. At least according to the model I'm going to show you, it's not 51%. So let me show you the model, and I'm going to write it as a probabilistic program, as a generative model, as a little program that we can run. Here it is. So what do? Well, I first guess what the vote share is. Okay, so across the population, there'll be a vote share. What proportion of the vote will go to me versus the other person? And then I model the poll by repeating Bernoulli trials of the vote share. So Bernoulli is a distribution which is a coin toss. It returns either true or false, let's say. And I repeat that to get a series of votes, which I'm then going to take 100 of to get back a poll simulation. Okay, and I also want to know, did I win? So I win if the vote share is above a half, if there's 2 people running. Okay, so this is a little very simple model which has 3 lines, and it returns 2 things. One is a list of 100 booleans, and the other is true or false, did I win or not? So it's a simulation that simulates a poll and returns whether or not I won in that scenario. Okay, yeah, it's a very simple model. You can imagine probably already ways of making it more interesting and more complicated and more realistic, or whatever. Right. So let's run it. So one way to, well, yes, before we run it, let's just say we can view this really as a specification. So we're talking about FACS, right? So this is a specification of a statistical model, but we can run it, and each time we run it, it will make random choices. It will choose a number between 0 and 1 for the vote share, and it will simulate the poll, so it will give us back 100 yes/no answers. So a very crude way to actually run it is what I'm going to call rejection sampling Monte Carlo. We run it millions and millions and millions of times, and each time we get a poll result and whether I won. And then what we do is we reject all the runs that mispredicted the poll. So all the ones where it didn't say 51 voted for me and 49 voted against me, we'll throw away those runs because they weren't the right thing. And we only keep the things from the simulation that actually matched the poll result. And then we ask what proportion of the remainder of all that we haven't thrown away say that I will win. Okay, so this is one way to run this model. It's very, very inefficient, but it's one way to run it. And we see then the answer, I think I've got it here, yes, is about 58% actually. The chance of me winning, according to this model, is 58%. Okay, so that's a model that gives you an idea of probabilistic programming. I'll come back to that model in a minute, but I wanted to have a little chat about probabilistic programming more generally. Probabilistic programming has applications, quite serious applications to election modeling and social science more broadly, but also biology, physical sciences too. And then going right down to sort of less traditional scientific things like machine learning. And of course, those connect very strongly. There are several languages which are very, very widely used, starting with bugs, which arose quite a while ago now, but more recently Stan and PyMC are widely used. Maybe some people here use these languages. Pyro is a newer one, which is, I think, quite popular. Then there are other languages I've missed out. Sorry if that's one of yours. But on the other hand, there are more experimental languages, and I've put listed some of them here, trying out different kinds of things that we can do. And the example I just showed you is in a library called Lazy Probabilistic Programming Language, which is a Haskell library. You can download it here, or you can also, if you see examples in this talk, you can go and look at them on the blog that's there on lazypeople.bitbucket.io. And we've just had that paper accepted to POPL, so very soon you'll be able to have a look at a sort of a paper about it as well. Okay, so that's probabilistic programming in practice, but I wanted to really talk about the formal aspects of it, but this is probabilistic programming in practice. Okay, and sort of to move towards the formal aspects and the connections between the formal aspects and the real issues, also practical issues, I wanted to sort of talk about abstraction. So forgetting about probability and statistics for a minute, we can talk about abstraction in traditional programming, and often we talk about high-level issues and low-level issues. High-level issues, maybe you want to talk about object-oriented programming, or if you're into functional programming, higher-order functions, abstract types, those sorts of things. At the low level, of course, we can talk about machine code, Boolean circuits. And I would argue that these things are interesting, both of them are interesting from both engineering points of view and foundational points of view. So, at the high level, we're interested in good software engineering, good practice. And so we want to reuse things, we want to organize things into libraries. So that leads us to high level constructs. We're also very interested in low level optimizations and so on. And on the foundational side, of course, higher order functions are beautiful because semantically they correspond via the Curry-Howard correspondence to proofs and propositions. So that's really exciting as well. And of course, these two things, there's a two-way street between all of these things that connect them all. Oh, I suppose low level, just to finish it all, low level at the foundation, I guess that's like complexity theory, theoretic results, but maybe tying into other kinds of things too. Okay, so I hope you agree that we can analyze high level and low level, both from engineering perspectives and from foundational perspectives. That's in traditional programming, but I think the same is true in probabilistic programming for statistical modeling. On the low-level side, in terms of sort of more practical issues, we could talk about Monte Carlo simulation. You already saw a bit of that. On the foundational side, we could talk about the foundations of probability, sort of as basic concepts of bets, Dutch book arguments, frequencies, decisions, and so on. But then at the high level, obviously all those good software engineering practices are important as well, of organizing things well and making code clear. But there are other things too. We could talk about infinite dimensional systems, and they have a particular statistical significance. Actually, we've already seen one. If I can jump back to this example, yes. I'm repeating the Bernoulli trial of a vote share. And repeat, actually, in Haskell, does that infinitely. It produces an infinite stream of votes. So that's an infinite process, if you like. It's returning an infinite dimensional system. So I'll talk a little bit more about that later. But that's something that's very, very important, like foundationally, but also maybe useful in practice. And then there are things like function spaces, which we'll talk about in a second, and higher abstract types. We'll talk about symmetries as well, quite a lot in this talk. Okay, so all of these things, all of these different angles are very, I think, very important and relate to each other. Okay, so that was a quick overview of an example of a voting model, and then a discussion of how I think the big picture looks with theory and practice in statistical probabilistic programming. But I wanted to delve in a little bit more into before I get into some more foundational issues, onto the sort of practical aspects of the low level. So just so you have a bit more of a flavor of what's going on. I'm going to talk a bit more about Monte Carlo simulations. So let's come back to this example, this illustration of a poll prediction. And maybe by running through this again, it will help you understand, if you didn't believe me, that the answer is 58% initially. Okay. So we did this crude rejection sampling thing where we threw away all the runs that mispredicted the poll. And that was very inefficient. And what we want to do is what everybody wants to do is do something more efficient. So what we do is to rewrite the program so that it doesn't throw things away. Now, what we know, got this here, yes, is that if we know the vote share, V, then we actually do know the likelihood of a poll, of the poll outcome that we have. Remember, we said 51 people said they'd vote for me, 49 said they wouldn't. And so the likelihood of that poll coming out from 100 votes taken from a particular vote share V is V to the 51, because remember, probabilities multiply. So V times V times V, 51 times 1 minus V to the power of 49, because there's 49 people who said they wouldn't vote for me. That's 1 minus V. So we can calculate actually the likelihood of the poll given the vote share, and that's this function here, V to the 51 times 1 minus V to the 49. And so what typically happens is this could be done automatically, or it could be done by hand. We translate this program, which was very inefficient in terms of simulation, into this one, which is much more efficient and then uses this score construct. I don't want to talk too much about it, but basically we weight the run of the program. So we don't actually throw anything away anymore. Rather, we weight the run by the likelihood of the poll given the data, given the poll data. So this, as I say, this could be done automatically or by some program transformation, or it could be done by hand. And now the whole thing is amenable to weighted Monte Carlo simulation, where we run it still maybe a million times or whatever. And each time we'll only get back, I'm sorry, the type here is wrong. We only get back a Boolean. And so each time, all we're doing is picking a vote share and then recording the likelihood. This thing here is basically V to the 51 times 1 minus V to the 49, but written so that we actually mirrors the code that we saw before. We run through all of the poll and either multiply by V or by vote share or by 1 minus vote share. And so what we do is each time we run, we pick a vote share and we get a weight, which is the likelihood. And now what we want to see, what's the weighted proportion of winning runs? So not how many of the runs were winning, but what's the weighted, using the weights that we've got, the likelihood weights, what's the weighted proportion? And this is equivalent to the rejection sampling method, but it's much faster because we haven't thrown anything away. Okay. Yeah, and it gives us back 58% again. Oh, well, let me just say before I sort of say a little bit more about that, what's really happening is that I think here we have this declarative model, but we're turning it down into something that runs a little bit faster. Yeah, if you're interested, the vote share is a number between 0 and 1. We've picked it to be uniformly distributed. We don't, let's say we don't know, and that's how we're interpreting that to mean. This is the likelihood function, v to the 51 times 1 minus v to the 49, this blue curve. And what we're interested in, the chance of winning, and that's the proportion of the area under the curve that's green. That's what's going to effectively happen when we run this weighted Monte Carlo simulation. You can see all these numbers are very, very small. E times 10 to the minus 31. So these are not probabilities, they're not normalized, but we just want to know the proportion of the area under the curve, which is winning. And that is 58%. So we're not interested in the mean of the likelihood function. The mean of the likelihood function is, I think, 0.51. We're not interested in that. We're interested in the chance of winning, right, which is different from the expected vote share, and that is the 58% value. Okay, so that's weighted importance sampling. Hopefully it gives you an idea, and we could go beyond that to much more advanced inference algorithms, again, running perhaps over these same declarative models. Let me carry on and talk a bit more about, more abstract constructions that appear in probabilistic programming. Seen two things in the chat. I don't know if that's just that's just the notices about the things. Okay, so yeah, I'm going to talk about function spaces, and then I'm going to talk about that for quite a while, and then I'm going to come back and talk about another thing, which is symmetries and names. And all of these things are familiar things that many people in foundations of computer science have looked at, but also connect very closely to probability theory, I think. So I'll try and emphasize that and how the two things connect. Okay, so let's look at some examples of functions and random functions. Okay, and again, we want to look at them really thinking of them from all these different perspectives. So here's a random linear function. So a linear function is determined by its slope and its intercept, ax plus b, let's say. And to make a random one of those, I sample a and b from, let's say, normal distributions. I used a uniform distribution in the last example. Let's use a normal distribution now. If you remember the normal distribution, it's this bell curve. So this is producing for me a pair A, B. It's a program that randomly generates a pair of real numbers, the slope and the intercept. Okay. Yeah, I'm going to use random functions to solve regression problems in statistics. So I'm going to, as a running example, use these data points here, and I'm going to ask which function generated these data points. They're not actually collinear, as you can see, so it wasn't actually a line, but let's say they're noisy observations of something, and then maybe we can think of that as being a line that generated them. Yeah, so it's all going to be a Bayesian thing, so we're not going to return a particular line of best fit. Rather, we're interested in a distribution on functions that generated these data points. Okay, so if I actually plot A and B, well, just as a pair of numbers, they're just a pair of numbers. They're not actually a line. So here I've just plotted A versus B, and you can see it's a multivariate Gaussian distribution. I've got 10,000 samples here. I really want to think of this as a function, though. So let's think of it as a function, and let's return an actual function. So in Haskell, don't worry if you don't know Haskell, I'm going to keep it quite plain. We can define fx to be ax plus b, and then return f. And that's now a genuine function from reals to reals. It's a one-dimensional linear function, ax plus b, where a and b are taken from normal distributions. And now I've taken 10,000 samples from that distribution or over functions, and I can now really plot them as functions from x to fx. I don't know how well that comes across on Zoom, so I just do 100 samples. So you can still see it. Looks like I've dropped a bunch of sticks on the floor or something. Yeah, I suppose it's interesting to think what's actually a good prior distribution on random functions. You see, maybe you were expecting a little bit more activity down here, and that's a matter for discussion, I suppose. Okay, so then what I do is I take that random linear function and pass it into a regression method. I won't go into this too much. Basically, I've got these data points, and I'm going to use the score that we saw before, but I won't spell this out too much because I don't want to talk too much about sort of simulation methods. I'm more talking about the modeling language here. Okay, but anyway, I run this regression model for example, in my Lazy People library. And it comes up with this distribution on linear functions. So you can see it's probably the line of best fit would be around there, but there's some uncertainty in which function generated these points. Okay, actually, I talked about weighted Monte Carlo. Maybe it's a good idea to briefly say one more thing, which is that we can do better than weighted Monte Carlo in this example too. And what this MH method does is it is better than that. So what it will do is each run, sometimes it will pick a new A and B from normal distributions. Sometimes it will keep the A the same as last time. And sometimes it will keep the B the same as last time. And that turns out to be advantageous for figuring out where's a really good pair A and B under certain circumstances anyway. So this is called the Metropolitan simulation method. And it works generally across a big class of probabilistic programs, including the ones that we're seeing here. Okay, so that's linear functions. Random linear functions. So what's going on really in this language? Let me say a little bit more about it. There's a type constructor, prob, which takes a type and produces a new type, another type called prob of that type. If you know about monads, it's a monad. If you don't know about monads, that's okay. I won't talk about them very much. For example, real num just contains numbers like 0, 3, pi, etc. Prob real num contains probability distributions, like the normal distribution, like the uniform distribution that we've seen. Prob bool contains probability distributions on the Booleans. In fact, the only only ones are the Bernoulli distributions, which are sort of coin tosses with a biased coin. We've also got parameterized distributions, and this might seem obvious or maybe not, but bear with me because it's not so trivial. So we've got normal, which really takes two arguments, a mean and a standard deviation, and produces a normal distribution. And we've got Bernoulli, which takes a bias and produces that biased coin. So those are things, let's just cut it down to things that take one argument for simplicity. So it takes maybe a standard deviation and produces a random distribution, distribution on the reals. But we also have random functions, like the random linear function that we've been talking about. And you see here the types of these two things don't differ by very much, but just putting prob in a different place. And these mean then totally different things. So what I find really illuminating about types is the way that they're really explaining what's going on, what kinds of spaces and structures we are talking about here. Okay, so prob real num, arrow real num contains random functions like random linear functions, but whereas parameterized distributions are functions from real numbers to distributions on real numbers. Okay. All of these different constructions can be spelt out using types. So that's all yes, so f here, for example, ax plus b is a function from real numbers to real numbers, but because it's wrapped up in this business where we're sampling a and b from Gaussians, then it becomes a random function. Okay. Oh, yes, we won't talk too much about this, but it's quite interesting to get into, is that we can also talk about random distributions. So distribution on the space of distributions on Booleans. And that's, yes, that's a random distribution. They're very, very important in Bayesian modeling. A bit of a challenge, though, is that although we can write all these programs very easily and the types will work, the Haskell type checker, for example, works fine, Ullman showed back in 1961 that the traditional measure theoretic foundations of probability don't support function spaces. So although we can easily write programs that provide random linear functions and other things that I'll look at in a minute, the measure theoretic foundation doesn't explain them at all. Okay? Or not properly anyway, in a sort of consistent way. So that's a challenge. I think it's quite exciting because it's saying that programming is sort of fine, and there's a problem with the underlying traditional mathematical models, and I'll come back to that. in a minute. But let's talk first a bit more about these function spaces, because we've only so far seen random linear functions. Okay, so something else that lives inside the function space is random programs. So if you've done a functional programming course, or you've written some functional programming, something you might have done is written a little calculator or a little evaluator. So we can have a data type whose inhabitants are abstract syntax trees, little programs involving real numbers, addition, multiplication. I've got an if, then else in there as well, and variables. And I can convert one of those into a function from reals to reals. If I know what the variable stands for, well, then that's just a constant function. Otherwise, I can evaluate an addition by using Haskell's addition. I can evaluate multiplication by using Haskell's multiplication, and so on. So I can write a little evaluator that walks over an abstract syntax tree. This is nothing probabilistic. This is just sort of first year functional programming. But now if I define something which I won't which I won't show you the code of it, which you can see online, which generates randomly an expression, then I can get hold of a random function. So for example, I randomly pick, am I going to do an add now or a multiply now, and then recurse. So I randomly generate some expressions. And I can then use those very quickly together with the evaluator to build a random function. And now I can then pass that to my regression algorithm, my regression function that I already talked about, exactly the same thing, run exactly the same Metropolis Hastings algorithm, and it will find me some random programs that could have generated these data points. So here we've got something, it was either, there's an if then else with maybe 3 branches. And if it was below 3, it's going to be constant. Otherwise, it's going to be this linear function, otherwise a different linear function. Or it could have just been a simple linear function, or maybe it was a one if then else. It's coming up with different random programs just by generating different things and then running Bayesian inference on these with the data set that we've got. Okay. I see Olaf has asked a question in the chat, but maybe I'll come back to that at the end if that's okay. Okay, so anyway, random programs are inside the function space. That's great. We talked about A and B being the parameters, and initially I said we want to think of those actually as the parameters over here. But come down here, over here, what are the parameters? Well, that depends on what random ingredients we used in building our random expression. So it's actually very complicated to see what the parameters are. And it's actually dealt with, I think, really nicely by the abstraction of programming, that we can still run Metropolis Hastings, which is randomly changing some of the parameters at different times, while hiding away all of that behind this prob monad. Okay, so there's other things in the function space as well, at least in lazy people. There's some Gaussian processes. So there's the Wiener process. This one is interesting because the parameter space is really big. So the Wiener process is like Brownian motion. It's nowhere differentiable. So it's really jumping about. And if you zoom in, it's going to jump in about even more. So the reason we could actually plot it or run any inference on it is because the viewport here is bounded. I mean, it does go on forever jumping about, but we've bounded the viewport, and also I plotted it at a certain resolution, and that's automatically caused the parameter space to be bounded, but it's still a very high dimensional thing. We don't really want to think of it, I think, as a vector of random choices. There are other Gaussian processes as well. Here's one with a radial basis formula. Okay, so lots of things in the function space. But I want to talk about one last thing, which is higher order functions, which also exist here inside programming as a very, very useful and powerful tool that most of you will know about, but which I think are something that we as formal methods people can offer to the statistics community. And so here's a simple one. Suppose something might quite want to do, I want to fit a piecewise constant function to some data points. So here is a piecewise constant function. Yeah, I want to fit it to some data points. I could also fit a piecewise linear function to some data points. Here's a piecewise linear function. What does the word piecewise mean here? what is piecewise? So I could talk about piecewise constant and piecewise linear, but what does piecewise mean? It's something that takes a concept and turns it into a piecewise version of it. Actually, we can define it. Well, let's first talk about random constants. I can start with random constant function. That's just a straight line somewhere. And then I'm going to define a function called splice. And what that does, I won't show you the definition. You can look it up. It's very short. Is to have some random points at which the function is going to change. And it's going to take a random function, like a linear function or random constant function. And then it's going to splice together draws from that random function to build a piecewise version of it. So we'll start with, here we go. We take a Poisson point process for the change points, and we pass in a random constant function that gives us back a piecewise constant function. But splice can also take in random linear, the function that we saw earlier, and make a random linear function. So this is a second order function. It's something that takes an argument, which is a random function, and it produces a random function as a result. Okay, so second order function splice, which takes a random function and produces a new piecewise version of it. Okay, so that's also all there inside the function space. And when you try and think what's the dimension or whatever of that, of a spliced function, then obviously that depends on the functions you're splicing and everything else. Okay, so that's function spaces. Now I want to talk a little bit about understanding them. As I said, Alman showed back in the 60s that it's impossible to do that using traditional measure theory, at least if you want to have function spaces satisfying the conditions that function spaces ought to satisfy. So let's talk about what we can do about it. So people often talk about the Curry-Howard correspondence. Let me remind you about that. And that's sort of what I want to motivate us. So Curry-Howard correspondence says we can talk about types and programs, but we should understand types maybe as sets or as spaces. Take the type of integers, that should be understood as the mathematical set of integers. A program should be understood, a functional program should be understood as a function between sets or between spaces, maybe a continuous one if we're dealing with recursion using continuity, for example. We could also view it categorically, if you like, where the types are objects of a category and the programs are morphisms. There's also a logical view, which I won't talk about today, but that's, of course, very important. And on the probabilistic programs side, I think that introduces a new row into this table in a way. On the mathematical side, I say probabilistic programs correspond to some sort of probabilistic measure, maybe in a conceptual sense at least. But we need to figure out what kind of measure that is and where does it live. So before I give a notion of space and a notion of measure that works, I just want to sort of talk about some desirable things. If I've got a theory of probability, what would I like it to satisfy? And if we're viewing probability from the lens of programming, what should it look like? So I talked about this random linear function, which is a random function. I've just changed it very slightly, so A has standard deviation 2, just to make it a little bit different. I can reorder the lines of the program. So I can first draw B from the distribution with standard deviation 3, and then A, or I can draw A and then B first. And I argue it doesn't matter. If I make one random choice with one hand and then the other one with the other hand, I could equally well do it with the one hand, with the other hand first, and then with the one hand. Okay, so that's an argument that probability ought to satisfy this reordering property. It shouldn't sort of remember whether or not we've already done a random choice. Of course, normally in programming, this is not possible. If I'm writing to memory or reading from memory, I can't reorder that in general. Sometimes I can, and that's very interesting, but I can't always do that. We can view this from a sort of a diagrammatic point of view by looking at data flow diagrams. And here I've just drawn this program more graphically. And you see I first do A and then I generate B, or I could first generate B and then generate A. And the data flow property is saying that these graphs are sort of, what matters is the topology of them. If I can move them around and keep the topology the same, then they should do the same thing. One other little thing is if I make another random choice C, which I never use, that was a bit silly, and I might as well not do it. So this program on the right, I would argue, is the same as the other two programs. So these are some desiderata of what sort of things should happen in programming in a model of probability, but expressed from a programming point of view. Or here's that from a graphical point of view. But we can also think of them sort of from a mathematical point of view. I can write this program on the left as integrating with respect to A and B. And what do we integrate? Well, we see whatever comes next, and that's going to return, let's say, ultimately a real number that we want to know the expected value of or something. That's K. And we do apply K to this random function. And so we're integrating that with respect to A and then B. Or if we integrate it with respect to B and then A, it doesn't matter. And this is called Fabini's theorem in measure theory or analysis, that we can reorder integrals. And that's true for probability measures. So I think that's a really crucial thing. And the idea that data flow in this way corresponds to Fabini's theorem, I think, is really nice. Okay. Also, this thing about cancelling out variables corresponds to integrating out a variable over a measure 1. It also connects to other foundational approaches to probability that I've put some references down here. Okay, so that's something we'd really like to hold, that we can see in the model, in the semantic model, that we can reorder the lines of programs. Okay, so let me show you a model then, Quasi-Borel spaces. Okay, Quasi-Borel spaces are a model which allow us to do all of these things. We've got probability in there, real numbers in there, function spaces in there, and the data flow property holds. Since it's a high-level talk, I just wanted to mention there are lots of other approaches to this, or not lot, but there's some other approaches to this. We could look at domain theoretic models, and they have some nice properties. This is quite recent work here. There are linear logic-based models, which maybe look a little bit different from this Haskell kind of formalism and type theoretic and monad-based formalism I'm looking at, but they're still very interesting. There are also models based on topological domain theory and other models too, I think. For now, I'm going to talk about Quasi-Borel spaces, which are a kind of space that we introduced about 5 years ago. It's inspired by several ideas from foundations of programming languages. Logical relations, something that some of you may know. And then there are other constructions around which are really useful for talking about function spaces in different contexts, which were really inspired by quasi-topological spaces, diffeological spaces, which are a kind of smooth analog, and sequential spaces. So let me tell you about Quasi-Borel spaces briefly. So this is getting a little bit more technical. A Quasi-Borel space is a set X equipped with a set of random elements. Now, the idea of Quasi-Borel spaces, yes, I'll be a bit technical, and then I'm going to, if this is too technical, I'm going to come back and talk about symmetries and names in a little bit more high level in a minute. Okay. But a Quasi-Borel space is a set X together with a set of admitted random elements. So the idea is that if I've got a random seed, typically what I want to do is, given a random seed, I can generate an element of X. And so a sort of a randomized element of X is a function from the reals to X, where given a seed, a real number seed, produces a result. But not all of those transformations from seeds to results, not all of those kind of codings of a random thing are legitimate or allowed. And so we carve out a set M of those. So a Quasi-Borel space is a set X together with a set of admitted random elements. Okay? So it's a little bit like, if you know logical relations, it's a little bit like that, except the arity of it is not just a binary thing, but a real number indexed thing. There are conditions that I want these things to satisfy that I won't show you just now. Okay, so the idea is then we're going to interpret the types of our language as Quasi-Borel spaces, and the programs are going to be interpreted as morphisms, functions between Quasi-Borel spaces that preserve this structure M suitably. That's all there is to it. But let's talk a little bit more, because I need to show explain how to interpret the real numbers, how to interpret probabilities. So I'm going to define a probability measure on a Quasi-Borel space just to be a random element. So a random element is something that's parameterized by a seed, so a function from R to X that's admitted in this set M. So that's exactly what a probability measure is. Now, sometimes different parameterizations of random elements actually describe the same kind of probability measure. And so we do have an equivalence relation on that. I'll skip over this to save a bit of time, but there's an equivalence relation on M, which gives us a notion of probability measure. Yeah, let's also talk about the real numbers. So the real numbers, we need to equip it with a set of admitted random elements. And those are exactly going to be the Borel functions. These, if you know a little bit about measure theory or probability, these are functions that are typically used for integration. So these are, but we're going to take all the Borel functions, not all the functions, just the Borel functions as the functions from in M for our space of real numbers. And that's why they're called quasi-Borel spaces, because the Borel sets are really, really important. Okay, so now we know how to interpret the real numbers. We know how to interpret probabilities. I haven't shown you how to interpret products and function spaces, but they have universal properties, so there's no choice, and actually works out really nicely. You can read more about it in our paper there. Okay, so that's quasi-Borel spaces, and they do satisfy the data flow property. We can reorder lines of programs when we interpret programs as functions between quasi-Borel spaces. Yeah, I'll just skip over this. I'm just trying to say it's connected also to other foundational issues in probability. Okay, but there was one, well, there are still some things open about all of this. I didn't want to suggest everything's finished. And one thing is this repeat command, which we saw right at the beginning. For a while didn't have a semantics in quasi-Borel spaces, which was quite annoying. So we had function spaces and everything else, but not repeat. Actually, we did have this repeat of a Bernoulli, but we didn't have repeat in general. So in general, repeat should take a distribution and produce a random stream of draws from it, an infinite stream of draws from it. So in traditional probability, repeat is defined by Kolmogorov extension, and it's very close to actually what Kolmogorov extension is. So I think that's really nice that this Haskell primitive is so closely related to a fundamental concept in probability. Just over the summer, just to keep it up, the talk a little bit up to date. So quasi-Borel space was 5 years ago, but just over the summer, I showed finally that repeat can be defined for a quasi-Borel space. We haven't published that yet. The proof was a little bit difficult, involving conditional expectations and some other constructions. Okay, so that's function spaces, and we've talked about ways of understanding them in terms of quasi-Borel spaces. I'd like to finish by talking about another aspect, which I think is really important in lots of areas of foundations of computer science, symmetries, but particularly symmetries and names. I know symmetries are important in model checking, things like symmetry reduction, and we want to focus on the names aspect of symmetries just now. But before we do that, we have already seen some symmetries in this talk, and those are the data flow symmetries. So remember I said I can reorder the lines of a program, or if I look at the graph, the data flow graph, I'm invariant under the symmetries of the data flow graph, moving things around. And this connects already back to ideas in statistics. De Finetti back in the 30s commented, I think, quite a deep observation that independence can be analyzed in terms of this kind of reordering. And this is called exchangeability in the statistics literature. So what's going on here? Here, obviously, I can reorder these lines of a program, and arguably it's because these normal distributions are independent, statistically independent. But sometimes I might write programs where I can reorder the lines of the program, but it's not, maybe not so blindingly obvious that they're statistically independent. And De Finetti argued or proved that this kind of reordering, exchangeability, really corresponds exactly with, via a representation theorem, to independence, in a sense. So De Finetti is talking about certain kinds of symmetry, but since then people have looked at all kinds of other symmetries, and there's work still going on now into different kinds of symmetries and representation theorems of these kinds. And I'll talk a little bit about that in a second. But let's flip back to the kind of foundation of the programming languages view and talk about names. So going back to the 80s, people have been talking about what is a name. Here's a a GUID, a unique identifier. I suppose it is on Twitter. Memory locations are kind of unique identifiers. And in both of these cases and in security, where we talk about nonces, the idea is it doesn't matter what name is being used. It's a pure name. It doesn't have any intrinsic meaning. It's just uniquely identifying something. Maybe our own names have that role. I don't know. My name's Sam. Here you can see that the people in Oxford spelled my name wrong on my badge. I don't know how you pronounce that. But my name's Sam. If I was born with a different name, like I don't know, Andre or Jonathan, then maybe everything would be the same. It would just be that we would commute all of history and change my name from Sam to Jonathan or Andre. Although I suppose it's not totally pure that the name Sam carries some information, maybe a little bit about where I live or where I'm born. So that's pure names are sort of an important thing to talk about in across computer science. But in sort of foundational methods, we've had all kinds of things in the last 20 years. People have looked at, or beyond that, people have looked at fresh ML and languages with name generation to study this kind of phenomenon. I suppose going back to Lisp's GenSym method. In automata theory, names appear in register automata. And PyCalculus was is a important concurrency language where names are crucial, when names take center stage, generating names and communicating on named channels. You know, and that's of course still an active topic today. I've put over here session types, but there are various things that people work on in PyCalculus still. And right, so that's names. What about names in statistics? I'm going to tell you about a place that I think names come up in statistics. It's dinner time. Let's talk about the Chinese restaurant process. So the Chinese restaurant process, I won't assume you know it, goes something like this. It's not like a Chinese restaurant I've been in, but people walk into the restaurant and sit wherever they like. They either sit at a new table or a table where there's other people, and they're more likely to sit with other people. So as they come into the restaurant fills up and more people sit at the different tables. The number of tables is unbounded. And there's two symmetries here, at least two. One is that the names of the tables are not important. Maybe I sit first at the one next to the door, but we don't talk about that. We just say it's a table. We need to know when two people are sitting at the same table or not, but we don't need to know, like, that was the first table that was ever used in this restaurant, things like that. The second thing is that the order in which I arrive in the restaurant doesn't affect the statistics of how many people I sit with. This is something that's not at all, I think, obvious or trivial, but it's a statistical fact. I haven't sort of formally defined this. You can look at a definition, for example, in the Lazy People website. But as I arrive, it doesn't matter when I arrive in the restaurant in terms of how many people I sit with. And so there's that data flow symmetry, that the order I arrive doesn't affect the statistics. So the Chinese restaurant process is used for clustering. So we talked about several statistical models today, including election prediction and regression models. Here's another one, clustering. So in clustering, I'm given some data points like these. I think there are 10 data points here, and I want to group them into clusters. So squinting at it, I don't know how many clusters you see. Maybe you see 3. But I wrote a Lazy People program. Again, I won't show you the code to try and keep the talk a little bit light, but it's not very long. It's about 5 lines. You can look online and see it. As each data point arises, then we think of it as a customer walking into the restaurant. And we think that the data points sitting at the same tables correspond to the data points that are in the same clusters. So I ran my clustering algorithm. It's a Bayesian model, so it gives a distribution over possible clusterings. But here's the most likely one that it found over the time I ran it, where it says there's these pink points, these blue points, and this green point here. Okay. So I don't want you to think that I'm just clustering them based on the x-axis. That's not what's happened. In fact, the green one's to the right of one of the blue points. Okay? They're genuinely walking. It doesn't matter which order we insert them. They're going to be put at different tables, and these are the clusters. So the names here are the names of, well, yes, I've got pink, green, and blue, but they're just colors as well. They don't mean anything. But maybe ultimately, we'd like to ascribe some meaning to them. Maybe this is some demographic, this is another demographic, and the blue ones are another demographic still. But for now, they're just pure names. They're exchangeable, they're symmetric. Okay. So to be a bit more technical for 1 minute, and then we'll look at another culinary metaphor and be a bit lighthearted again. We can go from this combinatorial description just with the tables and the colors and all the names of the tables and the symmetries that are there, down to a traditional statistical model as follows. So using a universal property of nominal sets, which is where maybe these things live, if they're names, if they're atoms, we can find a canonical map to measurable spaces whenever we pick a measurable space, such as the real numbers that has a measurable diagonal. So that gives us then a canonical map that translates this combinatorial description using symmetries and names and so on down to a traditional measure theoretic approach. And if we apply that to this scenario with the Chinese restaurant and the clustering, this gives us back the Dirichlet process, so a well-known process in statistics. So the connection between Chinese restaurant and Dirichlet was well known, but what I'm trying to say is that by understanding things in terms of symmetries and atoms and names principally, then we can get, and programming abstractions, then we can get hold of these processes such as the Dirichlet process in maybe a more canonical way. Let's look at one more example, since I think I've still got a couple more minutes. And this is the Indian buffet process, right? In case you weren't hungry enough. So the Indian buffet is a bit different from the Chinese restaurant. People walk in and they take some number of dishes, and they're more likely to take a dish that's popular, but the number of dishes is unbounded. So this person's just picked one dish, which is fine. The next person comes in and picks 2 dishes. Someone comes in and takes 3 dishes, right? But they didn't take the orange one, but they took 2 new ones, and so on and so forth. People keep coming into the restaurant and taking different dishes. So again, there's symmetry here, and this is something that needs some of it's not totally obvious, but the names of the dishes, I want to say, are names. They are pure identifiers. They are names, and we don't worry about this is the first dish that was ever eaten in our restaurant. Rather, we just say that's the red dish, that's the orange dish, that's the blue dish, and they can be permuted without changing what happens. The names of the dishes can be permuted without changing the statistics. And secondly, the order in which people arrive doesn't matter. So just because one person arrived first doesn't mean they're going to pick more dishes than another person, or that they're going to share more dishes than another person. So that data flow property again holds for this Indian buffet process. The symmetries are still there. Okay, right, so how can we use this Indian buffet? I'm going to use it to model, to follow actually an example by Navarro and Griffiths, where they also used the Indian buffet process, I think. Given some experimental data about what people say about which countries are similar, what can we say about the countries? So what happened was a psychological experiment. People were given pairs of countries, China and Japan, Russia and Libya. Are these countries similar or not? And just sort of psychologically, do they feel similar or not? And just ask to say yes, no. And I think a lot of people, I don't know how many people were asked, but a lot of people were asked, and they collected this information to get a notion of similarity between countries. Now they wanted to, now we can ask, using the Indian buffet, what are the features of the countries that make them different or similar? And the idea is to infer the features. So I wrote the model in lazy people. Again, it's only 5 or 6 lines. I won't sort of tie you with the code, but you can look online and see it. And it's a distribution over possible feature assignments, but this is the most likely one that came out from the time I ran it. And it's found these features. And again, these are just the machine found features, and they're really just names of features. It doesn't matter really which order we put them, or we shouldn't think of them as having any meaning a priori. But when we look at them, actually, we can start to think of them as having meanings. For example, I think the blue ones are the European countries. So it's figured out that European countries are similar. Another feature, I think these purple ones, we could say, I mean, I'm just coming up with this post hoc, that these could be ones that involved armed conflict recently. Okay, so it's 2006. Purple are sort of African countries, although Libya has not been included there, but yeah, these are psychological experiments, and maybe people didn't think of Libya as so African as, I don't know. I'm trying to say that they should do or they shouldn't do. I'm just saying that's what's come out. So these are features, they're not clusters, right? So Nigeria has both of these features. Okay, so that gives you an idea perhaps of the kinds of symmetry we can have there. And let's just jump back to that passage from the combinatorial model involving the restaurant, the Indian buffet. Oh, did I say how the Indian buffet happens? So sorry, the countries walk into the restaurant. Libya walks into the restaurant, Germany walks into the restaurant, Iraq walks into the restaurant, and they pick some dishes. And these are the dishes. That's how the metaphor works. Okay, so they pick the blue dishes or the purple dishes or the sort of mauve dishes. And the number of dishes they pick isn't fixed, and it doesn't matter which order they all arrive in the restaurant. Okay, so let's make that passage finally from the combinatorial model back down to the traditional model. And again, we're going to use that property that from nominal sets, we can pass down to measurable spaces given a particular choice for the atoms. And we do that here. So we had a perfectly simple combinatorial model with the symmetries and the names, and we end up with something called the beta process. So it's another process that's familiar from maybe more recent statistics, but quite important. So what I want to say, as a high level thing is, okay, these are two processes, Dirichlet process and beta process, that are by now quite well studied. But by just writing down new symmetries, using names in different ways, writing down new programs, we get new statistical models. And so this passage between combinatorial models described by programs and traditional kind of statistical measure theoretic models is there to explore. We can write programs that aren't just 5 lines long. We can write programs that are 20 lines long and explore maybe hierarchical structures. People talk about Chinese restaurant franchises, for example, and maybe graph models where there are links between certain things, not links between others, and so on and so forth. So I think that's a very interesting direction. Okay, so that's what I wanted to talk about. That's what I wanted to say. We've been looking at some programming language foundations for statistics and looking at them from all of these 4 angles, but primarily, I guess, at the high level foundational point of view, and hopefully giving you an idea that this does blur into the other aspects of these things as well. We've looked at some quick examples with election modeling, we've looked at regression problems, and then we've looked at clustering and feature abstraction. For the regression problems, we talked about function spaces, and down here for the feature extraction, we talked about symmetries and names. These are all crucial concepts in programming language theory, but I think they are also crucial concepts in statistics. Okay, thanks.
All right, thank you very much, Sam, for this really nice talk. Unfortunately, I don't think we have an applaud feature on this particular webinar. It used to be there a while ago, but now it disappeared. So I'm just going to give a hand of applause on everybody's behalf. And I think we can take some questions. We have some questions in the Q&A. People can add some more questions. And additionally, you can raise your hand if you want to ask the question verbally. So Sam, do you want to take one of the questions from the Q&A?
Yeah, so shall I? Yeah, okay. So Olaf asked, are there practical implementations of probabilistic programs that are not based on sampling? That's a very good point. One thing we might quite often do is to, if you can, to convert a probabilistic program to some sort of graphical structure, and then there are so-called message passing algorithms that work over that. The one that comes to mind just now is variational message passing, which is implemented in infer.net with Microsoft. But there are certainly other things to do. I mean, another thing which I didn't mention, which is perhaps interesting, is we can in that election example. Oops, that's gone. In the election example, we could talk about we ended up with a uniform distribution and then recording some Bernoulli results. Those are actually conjugate to each other in a statistical sense. So we can sort of do that symbolically. We could have solved some of that program. And so those conjugacy relationships, I think they also connect to message passing, but could help us to perform the inference like that. I mean, there are other things people have done is to translate the probabilistic program into some computer algebra, and then use computer algebra methods to solve these things. So yeah, so this, I think maybe Monte Carlo simulation is kind of the easiest thing to think about in a kind of sort of a basic interpretation, but certainly there are lots of other methods. Yeah. Yeah, Margaret West asks, what's the relationship between a name and an identifier? I think of them as the same, so I'm sorry if that was unclear. I suppose sometimes we talk about pure names and sometimes we talk about impure names. So I'd say maybe an identifier is typically a pure name, isn't it? I hope that helps. I'm happy to say a bit more if it doesn't. Olaf says, discardability and sampling don't seem to play well together at first sight. The program must be analyzed for usage of the random variable. I'm not sure what you mean by Rice's theorem applying here. But well, you wanted to say something, but maybe I'll just comment on discardability. I mean, it's true that we might not always know, obviously at compile time, whether we can discard a line of a program, and that's fine. I mean, the other thing is, of course, when we're doing our the technical detail is that when we're doing a Metropolis Hastings simulation, sometimes it does actually matter the order in which you put your variables, depending on how everything's set up, or having an extra variable in there might change how things work, how efficiently things work. So there's a sort of a conceptual idea that discardability and discarding lines and reordering lines should be allowed. But I mean, just as sometimes when you transform a traditional program, it might run faster or slower. The same is true with some of these inference methods. And that's really obviously quite an important idea, which has been taken advantage of by several people. Okay, so
just remind people that, excuse me, Sam. So if you have a follow-up to your question, you can also raise your hand if you want. And yeah, please, Sam, sorry.
Yeah, Francois asked to explain the intuition behind Armand's result. Armand showed that there can't be a Cartesian closed structure on measurable spaces. I think at some point I could have been able to give a quick intuition, but it's not just at the top of my head just now. Yeah, I mean, I suppose we can think of a random linear function as a two-dimensional, as a pair of real numbers. We can think of I guess a quadratic function, random quadratic function as three real numbers, and a random constant function as one real number. And I mean, so all of these are totally fine. There's no sort of measure theoretic obstacle to any particular class of function. The problem is trying to include all of them in function space. Yeah, okay. I mean, to sort of really argue it, you need to get into sigma algebras and the Borel hierarchy. So yeah.
Okay, while we are waiting for potentially other questions, I take the opportunity to ask a question too. So in the non-probabilistic world, when you introduce a denotation semantics, you have these various means of validating it. One of the most important ones is by operational semantics. So you want at least soundness. Yeah. Ideally, you want full abstractness, full abstraction. Is there any counterpart in the probabilistic world for such properties? For example, your Quasi-Borel space semantics, does it have I guess it validates some operational model?
That's right. So we did make, because I mean, that's kind of the one of the points is that an operational semantics for probabilistic programming is quite easy in a way, especially if we think of it in terms of Monte Carlo simulation. You just run the program when we know how to run programs and see what comes out. So we then did show an adequacy result between the Quasi-Borel space model and the sort of a simple operational semantic model. And other people, I think, have looked at other kind of soundness properties of operational semantics too, or connections between different operational semantics models. I'm thinking of Ugo Del Lago and some with Andrew Gordon and Johannes Bergstrom and Marcin Simczak. So that's certainly a good thing to do. I mean, it's not fully abstract, and I don't know whether you'd want that, but we did actually look at, it's interesting, we could include, since names, if we think of names as being randomly generated, we can encode fresh name generation using randomness. And we did that last year at Popple, and we found actually this is fully abstract up to, well, depending on how you count the orders, maybe up to second order. Which is even better than the nominal sets model. So it's not too bad.
All right. Okay. Thank you. Some more questions are popping up. So Nobuko has a question. Do you prefer that I read it, or do you want to read it? Whatever is.
Okay. Yes, that's a good point. So Nobuko is asking, symmetries and names are a good fit with concurrency and optimization. How can they contribute to gaining performance of computing probabilistic programs? Yes. So I mentioned message passing. I was thinking of, or I don't know if that's what you're talking about, but I mentioned message passing inference, which is maybe different from message passing and concurrency, or maybe related. I wouldn't like to really say, but how do symmetries come in? Right. So I think the symmetries allow us to say that certain programs are equivalent to others, and therefore to right. So when we're running, for example, a Metropolis Hastings simulation, it's very useful to know whether if I resample one part, does that mean I ought to also resample another part? And so if I know everything's symmetric, that tells me that I don't have to do that and can make things much more efficient. So that's one point, I think, where symmetry is really important, because the symmetry is telling us, if you like, that the things are independent. It's giving us a sense of independence. And so we're able to avoid or take advantage of that when we're doing inference algorithms. Yeah. Have we studied speed? I don't know if anybody's really studied performance and speed. So I mean, one thing I ought to say about speed is when we when we try and run an arbitrary program that's written in quite a complicated way with branching and all kinds of other things, maybe different random choices, the number of the dimension is unknown or changing. Speed, I mean, what matters is whether we are seeing the posterior distribution. We know typically by Monte Carlo results that in the limit, we will see the posterior distribution, but we probably won't know. We might not be able to say whether we're actually seeing an approximation of it yet. And so speed maybe means speed of convergence of a Monte Carlo simulation towards some posterior distribution. And that's, I think, unfortunately, in the general case, very hard to figure out. So yeah. Okay.
More questions coming up.
So Olaf is asking about domains. Yeah, so there is, I mean, the work on domain theoretic semantics, well, there's two angles on, this is a bit technical and I'm not sure I'll say it right just off the top of my head, but there's two angles on domain theoretic semantics for this, at least two. And one is just using traditional domains, but not picking sort of algebraic domains or continuous domains, but allowing ourselves to go outside that. And I think that was, for a long time, domain theory was stuck on semantics of probability because we wanted to, the so-called Young-Tix problem was about finding out whether there's a power domain on a Cartesian closed category that contains, I'm going to say this wrong, I'm going to say Scott domains, but I'm not 100% sure that's how they phrased it. So the recent ideas have been just to forget about that and just allow arbitrary CPOs as a starting point, and that's worked quite well. Yeah. So the other approach is topological domain theory, QCB0, and so on, which I'll perhaps leave there.
All right. Before we go to the next technical question, so Vicky highly enjoyed the talk and would like to see the slides. If this is okay with you, Sam, to share the slides after that.
Sure.
And we will definitely make this talk available on YouTube. Okay. So this will be available to all the registrants and I guess to the whole world. All right. And there's another question by Harsh Beohar. The relation between...
Yes, is there a relation between the category of quasi-Borel spaces and category of measurable spaces? So yes, there is indeed. So for any measurable space, we can take, I haven't got the slide up now, but we can take M was the admitted random elements. We can take those to be the measurable functions. And that converts a measurable space into a quasi-Borel space. From a quasi-Borel space, we can regard it as a measurable space by saying that we build a sigma algebra by looking at the maps into the booleans into 2, and those are the measurable, the events. And that forms an adjunction between quasi-Borel spaces and measurable spaces. So we can move back and forth between the sort of traditional view and this quasi-Borel space view, which is more well behaved for function spaces.
Okay, and Margaret would like to see, so yes, the video will be made available, a brief to some of the papers you mentioned, so a list of the relevant papers for this talk. Probably they can be included in the slides or in some other way, if, yeah.
Yeah, right, sure, I had some references in the slides, I'm not sure if they were too small to come across, but yeah. Okay,
so they will be available on the slides. And then there's a question from Mark, and then Jonathan, I'm not sure if you will have a question or...
No, I can certainly put links to any relevant papers on as well. So if you'd like to send a list of very pertinent papers with web links, that would be great.
Okay, thanks.
All right, okay, sounds good. And then there's another technical question from Mark.
Does your probabilistic programming environment allow the random values to be recorded so identical results can be obtained by someone else wanting to reproduce those results? I think most would. Mine doesn't currently, but yeah, typically you'd want to have, I guess, if you wanted to have some reproducibility thing, you would want to say what was the seed that you used to generate a particular thing. Now, I mean, I think I'm not sure that that's such a good practice from a sort of a Bayesian point of view, because really you ought to be getting the same posterior distribution regardless of the seed that you start with. And if you get a different posterior distribution starting from different seeds, it suggests that you haven't been running your Monte Carlo simulation for long enough. Yeah.
Okay.
Yeah.
If I can also ask another quick question, so I take advantage of any pause to ask my own questions. So with great progress in semantics and in the semantic understanding comes great progress with verification techniques. Can you talk a little bit about the verification techniques that are emerging, let's say in reaction to your semantic contributions?
Yes, that's a good point. There was certainly, I meant to mention that, but I didn't. I forgot to put the slide in. But yeah, there's been certainly some interesting work on program logics for probabilistic programs, verifying various properties expressed in various logics of probabilistic programs. I'm thinking of work by Marco Gabordi, and I've forgotten Justin Su, I think, and maybe Gilles Bart, and I'm sorry for the other co-authors. Yeah, so that's been very interesting. I think one point though is that because with all this randomness around, maybe it's not always the case that you just want to prove some sort of correctness result of maybe the same kind that you want traditionally. I mean, for example, often we prove termination in work on verification, and I to a statistician, I want to prove that your model terminates. They probably wouldn't be very interested, because they just run the model, and if it doesn't terminate after a while, then they kill it and run it again. So, but there are certainly properties they are very interested in. I think they could be different properties. For example, convergence of Markov chains.
Okay, and I guess a sub question here, because you have these nominal models and you care about symmetries. I'm wondering whether reasoning techniques developed within nominal logic, to which extent they would be generalized to apply here. I guess you are dealing with infinitary structures, not necessarily finitely supported, but still you want to reason about the various symmetries. Is there any reuse of nominal logic techniques?
Yeah, that's possible. Yeah, I mean, these are finitely supported structures. Yeah,
they are finitely supported.
I would say so. It's a bit unclear, perhaps, because if I run the Chinese restaurant for some finite amount of time, which I'll only ever be able to run it for a finite amount of time, the number of tables will be finite. So the number of atoms or the number of tables is going to be finite after a finite run. But yeah, I think also we'd like to maybe consider an infinite abstraction of that. Yeah, but it's certainly, I haven't thought much about the nominal logic yet, but that could be an interesting angle. Yeah.
Okay. We have quite a lot of questions. Are there any more questions from the audience, either in writing or verbally by raising your hand? Okay, so
Harsh has wasted.
Oh yeah, so I think you have already addressed that. He has raised the hand. You're saying. We have a hand raise. I cannot see it. You can see somebody. We can see Harsh. Oh right, I see him now. All right, Harsh. Let's see if we can. Yeah, we can hear you now. Go ahead, Harsh.
Okay. Thank you, Stam, for the talk. I just want I'm coming from a co-algebra literature. Would you suggest there are any interesting functors on the quasi-Borel spaces that we should study? For example, like label Markov spaces are like co-algebras of Giri monad or something like that.
Yes, exactly. Yes. So there is a probability monad on quasi-Borel spaces, and that's definitely one to study. Actually, I first talked about this nominal thing at CMCS, algebraic methods in computer science, a few months ago, and there I was talking about coalgebras as well. So I'll be happy to share the slides from CMCS with you if you're interested. Yeah, certainly lots of coalgebras. So for example, I talked about De Finetti's theorem, which says exchangeability corresponds to independence or something. That really is I would say a coalgebraic result. It's a result about the final coalgebra of a certain endofunctor, and that's what.
It'll be lovely to read this. Yeah. And a related question, more from a operational side. You were talking about program equivalence. Is there a notion of bisimulation equivalence also on these probabilistic programs that one should, because right now everything is deterministic, so maybe that's not so interesting for the ones you describe in today's presentation, but are there any proposals of probabilistic bisimilarity or something?
Yeah, I mean, of course, there are notions of probabilistic bisimulation going back to Larson and Skoo and so on, and looked at coalgebraically by various people. I didn't show here some of the kinds of program equations I've been looking at. But I was actually surprised. There were some examples of programs that I felt should be the same, connected to De Finetti's theorem and polyazerne, and that's in the paper, but where I expected to be able to easily use coalgebraic bisimulation to show that, and I actually found it was not so immediate. So maybe it's more connected with kind of trace equivalence than bisimulation. In some sense.
Okay.
All right. It turns out that not only that I'm not multitasking, but I'm not even bitasking, so I cannot follow the Q&A and the chat and the participants at the same time. So it looks like there are no more questions in the Q&A and any hand reason. All right. So I think then we can end it here. Thank you very much, Sam, for the great talk, and to the participants for the very interesting questions. And I think this is to be continued. So there's a lot of follow-up reading and digesting on the things that you touched upon here. So yeah, thank you very much again, everybody. Please don't forget to consider the Peter Landin seminar on the 6th of December. And yes, I think, yeah, you all have a good evening, and thank you very much for coming again.